Hello there, AP Environmental Science class. Welcome to my lecture on Chapter 20, Climate Change. You guys have made it. The final chapter of the book. Here we go. Again, Chapter 20, we are going to talk about climate change. So there are 61 slides to this lesson. So I will once again break it up into two parts, Part 1 and Part 2. So here we go. Again, the final lecture of the year, Chapter 20, Climate Change. Here we go with part 1. All right, so starts off with a core case study talking about the melting ice in Greenland. So Greenland is one of the world's, or is the world's largest island, and is mostly covered by ice glaciers. However, the glaciers have been melting at an accelerating rate in each summer, and we believe atmospheric warming or global warming is a key factor to the acceleration of these glaciers melting on Greenland. Greenland's ice loss is responsible for nearly 1/6 of the global sea level rises that we've experienced over the past 20 years. There we have a picture of Greenland. Obviously, what you see in white is the glacier that covers most of the island. And what you'll notice is that the sea ice that has melted during the summer in 1982 on the left, that's in red, is much smaller than the sea ice that melted during the summer of 2012, which is the red on the right. So what are we seeing here? This is indirect evidence of accelerating climate change or increase in global warming or global warmth, right? Because if the globe wasn't warming, then the ice would not be melting. So because we're seeing the ice accelerate in its melting, and not only here in Greenland, but we're seeing it at the North Pole and in Antarctica as well. Again, we can conclude that the Earth is warming too fast, and that's why this ice is melting that quickly. So, how and why is the Earth's climate changing? Well, scientific evidence strongly indicates that the Earth's atmosphere is warming at a rate that is likely to lead to significant climate change. So just a review of some terms. Weather is short-term changes, right? What happens day to day, maybe 1 or 2 weeks. Climate is the average weather conditions of a particular area over 30 years. We're talking decades, centuries, things like that when we talk about with climate. So unfortunately, we are seeing our climate change, and the issue here is that the climate is changing at a faster rate than organisms can keep up, right? What we'll talk about is that the climate has changed on planet Earth throughout Earth's history. We've had warm periods, we've had ice ages, back to warm, back to ice ages. But the key is that it's always been a slow change, so that creatures have been either able to evolve or maybe migrate to a new area if the climate changes where they're living. But again, it happens over a long period of time, so organisms are able to adapt. Unfortunately, what's going on right now is the climate change is happening so fast, most likely because of the increase in greenhouse gases that we're putting into the atmosphere. We'll talk more about that in a couple of minutes. Because it's changing so fast, creatures are not able to adapt. They're not able to evolve. They're not able to migrate. And as a result, we are seeing mass extinction. Maybe, again, we've spoke about it in a previous unit, how we are most likely in the 6th mass extinction currently. So talk about climate and the natural greenhouse effect. Now, this is actually very interesting. When you hear the greenhouse effect, many times your first thought is a bad thought. The greenhouse effect is actually good. It's actually a natural process where heat-holding gases, which we call greenhouse gases, absorb infrared radiation or heat that the Earth re-radiates, right? The Earth, it's heated by the sun heats the ground, and then that ground re-radiates heat in the infrared part of the spectrum. These special greenhouse gases trap that infrared radiation, keeping the Earth nice and warm. If we didn't have the greenhouse effect, guys, the average temperature of planet Earth would be 0 degrees Fahrenheit. That means we would be an ice ball planet and there would be absolutely no life on this planet. Because we have a greenhouse effect, our average temperature is 59 degrees Fahrenheit on this planet. And so that has kept us nice like a greenhouse and allowed life to form on this planet. The problem is that we as human beings, because we're throwing more of these greenhouse gases into the atmosphere by burning fossil fuels and by other reasons we'll talk about, we are creating a runaway greenhouse effect, or what I like to call a greenhouse effect on steroids. It's a stronger greenhouse effect than the natural one one that Mother Nature provides us, again, part of Earth's natural capital. And because of that runaway greenhouse effect, now we are seeing global warming. So what are the three main greenhouse gases that you need to know? Carbon dioxide, CO2, methane, CH4, and nitrous oxide, which is N2O. Now, believe it or not, the number one greenhouse gas in capturing outgoing infrared radiation is water vapor. Believe it or not, water vapor traps more outgoing infrared radiation than these three greenhouse gases I just told you about. Why, though, don't we talk about water vapor? Because we as human beings are not changing the amount of water vapor in the air. The amount of water vapor is the amount of water vapor. The amount of water on this planet has not changed for millions of years. So it's not an anthropomorphic. That's a word for you. Anthropomorphic means created by humans. Water vapor is not created by humans. So that's why we don't talk about it, even though it is the number one greenhouse gas in a sense of trapping the most heat. We talk about, however, carbon dioxide, methane, and nitrous oxide because we, as human beings, are adding carbon dioxide, methane, and nitrous oxide to the atmosphere, and as a result, increasing the greenhouse effect. So that's why these are the three that you need to know, even though I just want you to know that water is actually the most important, or at least the largest trapper of this infrared radiation. But again, it's not anthropomorphic. It's not made by humans, so we don't necessarily care about it because it's not changing. What we care about is the carbon dioxide, and the methane, and the nitrous oxide that we are actually increasing the amount in our atmosphere. And as a result, we're seeing the Earth warm because the greenhouse effect is getting stronger than it should be. Historical changes in the amount of carbon dioxide in the atmosphere correlate to the change in global temperature. We'll look at that coming up. So here are just some atmospheric lifetime and warming potentials for the three major greenhouse gases. So you'll notice the lifetime nitrous oxide stays there forever, 114 years. Carbon dioxide varies around 100 years. Methane about 12 years. You'll notice a nitrous oxide, okay, so this is the warming potential as multiples of carbon dioxide. So carbon dioxide actually, when it comes to warming potential, is actually the least the one that traps the least amount of heat is actually the carbon dioxide, even though we hear about the carbon dioxide the most. The methane traps 25 times more heat than carbon dioxide, with nitrous oxide trapping 300 times more heat. It's just we hear about carbon dioxide a lot because that's the one we're throwing in the most compared to the methane and the nitrous oxide. But actually, the nitrous oxide has a much more warming potential than does the carbon dioxide. So just understand this chart and what it's telling you. Again, the atmospheric lifetime and warming potentials for our three major greenhouse gases. All right, so there has been climate change in the past. We have talked about that. I mentioned we've gone through ice ages, we've gone through warmer periods. So there are natural factors that can cause climate change, like massive volcanic eruptions, changes in solar input or the amount of energy we get from the sun, changes in Earth orbit, changes in the tilt of Earth, something called the Milankovitch cycles, global air circulation patterns, changes in the amount of ice, the albedo, changes in the greenhouse gases, and changes in ocean currents. These are all climate changes that has happened with natural factors, okay? And again, here's the atmospheric levels of carbon dioxide and changes in average global temperature, okay, of the atmosphere near the Earth's surface over the past 400,000 years. Data was attained by analyzing some ice cores removed in Russia. So what you'll notice is on the top here, we're looking at carbon dioxide concentration, and on the bottom, we're looking at temperature change. And you'll notice there's a direct correlation. When the carbon dioxide increases, the temperature increases, right? So we had an increase in carbon dioxide, looks like about 330 million years ago. That caused an increase in temperature. Our carbon dioxide then dropped, then it increased again about 240 million years ago, and we see an increase in temperature. Then the carbon dioxide dropped, then it increased again about 135,000 years ago, and we saw an increase in temperature. Then the carbon dioxide began to decrease, and then look how it's increased over the past 100 to 200 years. That's a straight up spike. It's never been this high before, and you'll notice the Earth again showing that warming. So again, this is key, showing us that the amount of carbon dioxide in the air, the more you put in, the warmer your temperature. And that's been the case over the course of Earth's history. Now, most of these increases in carbon dioxide dioxide in the past, obviously, have been natural, right? Increases in volcanic eruptions. Some of the other things that we talked about, forest fires, things like that, that could potentially increase the carbon dioxide naturally. The problem is the past 150 to 200 years, that carbon dioxide increase has become unnatural. And that's because we are creating or putting more carbon dioxide into the air by burning fossil fuels. And as a result, we're seeing the earth warm, and the earth continues to warm. So again, direct correlation, guys. We increase the carbon dioxide in the atmosphere, you're going to increase the global temperature. And that's been the case back through a couple of 100 million years looking at the data. So that's historical. Now let's talk about current atmospheric warming and climate change. Climate change is happening now. Between 1906 and 2016, Earth's temperature rose by 0.94 degrees Celsius. So you think that's not a lot, but when you factor in it's the overall temperature of the entire globe, that it's almost risen 1 degree Celsius in about 100 years, that is way too fast. Again, that is not natural. The natural would have taken hundreds or thousands of years to see that temperature increase by 1 degree. Here it's happening in just 100 years. The 10 warmest years on record since 1861 have taken place since 2005. So since 2005, we have had the 10 warmest years on record since we really begun taking good temperature records in the mid-1800s. Arctic ice has been shrinking since 1979. That's a fact. Glaciers are melting. That's a fact. Permafrost, all right, what is permafrost? In the Arctic area, the ground stays permanently frozen most of the year. Well, the permafrost is melting, and as a result, rising sea levels are also reducing coastal areas. Carbon dioxide and methane levels, again, they've risen sharply. That's a fact. Terrestrial organisms have migrated towards the poles and up mountains where it is cooler because they can't handle all this extra warmth. Again, that is a fact. We are seeing terrestrial organisms do that. So what are the roles in humans having on this current atmospheric warming? Well, the burning of fossil fuels, deforestation, and agriculture has led to significant increases in greenhouse gases, right? It's all coming together. We've talked about fossil fuels. We talked about deforestation. We talked about industrialized agriculture this year. And now we're tying it all together here in the final chapter. It's all leading to a significant increase in those greenhouse gases. We also have an increase of methane, again, more potent than carbon dioxide, right? About 25 times more or so potent than carbon dioxide from a warming potential. And we get that increase from livestock, rice production, and natural gas production, like we spoke about in previous chapters. U.S. has the largest per capita carbon footprint. That was we did early on in the year, right? We looked at our own carbon footprints. We have that word affluenza, right? We're sick on our affluence. Carbon is added to the atmosphere faster than the carbon cycle can remove it. Again, in the olden days, before human beings, carbon was added, carbon was taken away, right? Trees sequester carbon, right? We said the oceans sequester carbon. We've talked about this. Well, now, unfortunately, we're adding it too fast, and so this is why the carbon dioxide levels have increased. Humans have also cut down forests, which, again, is a sink, our way that carbon is sequestered. We're cutting them down. Changing climate is much faster than change induced by natural factors. So climate scientists agree now that climate change is happening. Human activities play a significant role in climate change. The average atmospheric temperature are likely to continue to increase, and immediate action is possible and affordable and would bring major benefits. So what I want to talk to you real quick about is isotopes of carbon. So you notice, you know what an isotope is, right? It has different neutrons in the nucleus, right? Proton, electron makes an element, right? And then the neutrons make the isotopes. So something that we've looked at, people say, well, the added carbon is just because there's extra volcanoes that have been erupting or things like that. Believe it or not, carbon that is produced naturally by erupting volcanoes is a different isotope of carbon compared to the carbon that humans create by burning fossil fuels. We have looked at ice cores. We've looked down through the years, okay? When you look a couple 100 million years ago, 10,000 years ago, etc., the only carbon you see are the isotopes that are natural carbon, produced by volcanoes, produced by burning trees, things like that. Right about 1880 or 1890 or so, when you look at those ice cores, the carbon all of a sudden becomes the man-made isotope of carbon. And that's the only carbon that we see present from about the late 1800s to the current time in these ice cores. So how can you say that it's natural carbon that is producing global warming? It is not. They're different isotopes. Okay, it's the smoking gun. We wanted the smoking gun. We found it. We found it in these isotopes. The isotopes of carbon that we've seen over the past 150 years is the isotope of carbon that the humans create with burning of fossil fuels. Period. So you can't say the increased warming we've seen over the past 100 years is because of natural causes. It's not. It's because of the carbon that we are putting into the atmosphere at an uncontrollable rate. And we need to stop it, or we're going to be in big trouble. And again, that's the smoking gun. Just look at the isotopes. Fossil fuel lifestyle has led to serious problems. It's led to air pollution, climate change, and ocean acidification. Scientists use models to make projections about future trends. And again, the future trends show if the carbon continues to increase in the atmosphere, that the Earth will continue to warm. So what is the role of the sun in the current atmospheric warming? Well, the cause of warming cannot be increased solar output, right? Because believe it or not, the solar output has actually dropped slightly during the last few decades. Don't worry, the sun goes through these cycles, but actually the past few decades when we've seen the most global warming, right? 10 of the warmest years have been since 2005. The sun's output has actually dropped. So don't tell me it's the sun. Troposphere has warmed while the stratosphere has actually cooled. So again, if the sun was the issue, the stratosphere would warm because ozone is in there absorbing ultraviolet radiation in the stratosphere. That hasn't happened. The stratosphere is actually cooled. So again, it can't be the sun. The atmosphere is heating up from the bottom up, not from the top down. If it was the sun, it would be from the top down. It's coming from the bottom up, and that tells us humans are the ones creating the problem. The effects of oceans on current atmospheric warming. Well, oceans are a sink for carbon, right? We went through this in a previous unit. Most stored as carbon in marine algae and vegetation, or in coral reefs and bottom sediments. Also absorbed heat from the troposphere. This has resulted in ocean acidification. And how do we know? Because we've seen the corals get bleached, right? We spoke about this in a previous unit. The corals are dying because of the carbon that, again, is too much of it is being stored. Here is the effect of oceans on current atmospheric warming, or this is basically just showing the rise in global atmospheric levels of CO2. Again, look at that increase. That's been a direct increase since 1960. This is the carbon dioxide concentration, okay, in the atmosphere. And you're going to notice that the atmospheric levels of carbon dioxide, while on a year-to-year basis fluctuate up and down, you'll notice this trend since 1960 has been directly up, and we need to unfortunately change that trend. What effects do cloud cover have on atmospheric warming? Well, net effect of cloud cover change is likely to increase warming. Cumulus clouds actually reflect light back into space. Cirrus clouds insulate Earth, increasing cooling. So, unfortunately, the net effect is going to increase warming. If we see less clouds out there, there could potentially be more warming. So, cumulus clouds on the left are thick, relatively low-lying clouds that tend to decrease surface warming by reflecting some incoming solar radiation back into space. Cirrus clouds are thin and float at high altitudes. They tend to warm the Earth's surface by preventing some heat from flowing into space. So what we're saying is that we may see more cirrus clouds compared to cumulus clouds, and that could also increase warming. What about the effects of outdoor air pollution? Well, light-colored aerosols reflect incoming sunlight. However, dark particles like soot absorb heat. So most likely, the outdoor air pollution, again, when it comes to this reflection, may not really affect climate change. But if we continue to put more coal, if we continue to burn more coal leaves that black kind of sooty residue. So if we unfortunately get more of that on the Earth, that could absorb more radiation, and that could potentially increase global warming. So what are the likely effects of a warmer atmosphere? Well, the projected change in temperature could have severe and long-lasting consequences, like increasing flooding. We spoke about the rising sea levels because of the melting ice, shifts in the location of croplands and wildlife habitats, but again, too quickly of a shift. Nature can handle a slow shift, right? Evolution, we can deal with it. Migration, the problem is when it happens really quickly like it's happening now, it's very, very hard to adapt. In addition, there could be more extreme weather. So, Temperatures are rising rapidly. Climate change tipping points. This is the threshold beyond which natural systems will recover. So if we get a global temperature rise of 2 degrees Celsius, which is another degree, right? We've gotten to 1 degree. If we go another degree, or if carbon dioxide concentrations rise above 450 parts per million, our models that project out what's going to happen say that our natural systems will never be able to recover if this happens. If we don't get to these thresholds, then we can recover. And that's the key right now. The key is we're approaching some of these thresholds. So we need to stop it, or at least slow it down, so that we don't get to these climate change tipping points. And again, the harmful effects will be unevenly distributed. So the reduce food security, increase poverty, and social conflict. Unfortunately, when climate change, as it continues, usually who feels the brunt of these effects are poorer, more underdeveloped nations and peoples, unfortunately, because they can't handle it, right? They can't put air conditioning in, or if their area gets too hot, or can't put, heat in if their area gets too cold, or if they used to grow crops that now can't grow. If you're poor, you can't go out and buy your food, right? So you're kind of stuck. And so again, unfortunately, these harmful effects will be unevenly distributed. So rapid atmospheric warming could have serious consequence. Again, so if we get that atmospheric carbon over that 450 parts per million, we're in trouble. That's your tipping point. Could have the melting of all Arctic summer sea ice. You could have the collapse and melting of the entire Greenland ice sheet. Severe ocean acidification, which would mean a collapse of phytoplankton populations, which is the bottom, but the most important part of the ocean food web, and a sharp drop in the ability of the oceans to absorb any more carbon dioxide. Massive release of methane from thawing Arctic permafrost and from the Arctic seafloor. Believe it or not, when you thaw that permafrost, you're actually releasing methane that has been trapped for millions of years in the permafrost, and that's adding to the methane, or another, that greenhouse gas. Collapse and melting of most of the western Antarctic ice sheet, and severe shrinkage or collapse of the Amazon rainforest. These could be some of the serious consequences if we reach that tipping point. This is talking about the big melt. You'll notice the average minimum ice cover from 1979 to 2010. This isn't at the North Pole. Covered this entire area here outlined by yellow. On September 16th, 2012, this was the minimum ice cover. So you can see in just, what are we talking about here? We're talking about 30 to 40 years, right? Look at this minimum sea ice Arctic extent, and the average sea ice by volume just continues to drop. Again, there are fluctuations, but the overall trend is down. If you're dropping the sea ice, unfortunately, you're rising the sea levels, because that water has to go somewhere. And where is it going? It's going into the oceans. So the increased melting of ice and snow is actually a positive feedback effect. We talked about these feedback effects in a previous chapter. Remember, positive doesn't necessarily mean good. It just means as you melt more ice, right? So ice is light colored, right? And it reflects solar energy, right? It has a high albedo. But when you melt the ice, what are you doing? You're reducing the albedo, which then causes more energy from the sun to get absorbed by the surface, right? It's not being reflected. If you absorb more energy, you're heating up the surface, you're melting more ice, which then causes you to absorb more energy, which warms things up, which melts more ice, which absorbs more energy, which warms things up, blah, 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 right? That's your positive feedback loop. And that's what's happening with this accelerated polar ice melting. It's making it even faster, right? So the complete melting of summer sea ice may happen by 2050. Again, these are those climate tipping points, and the changes in Arctic seawater temperature actually influences the jet stream, which again influences the type of weather that certain areas have. And this is why we could be seeing more extreme weather in different parts of the world than we're used to. In addition, mountain glaciers are shrinking. They play a vital role in the water cycle, so we may be messing with that as well. This slide talks about what I just spoke about a little bit ago, the methane emissions from thawing permafrost. Again, what is permafrost? Frozen soil in the northern hemisphere. Climate change is projected to thaw significant amounts of that permafrost already happening in Alaska and Siberia. Not only does it release methane when you thaw this permafrost, but also carbon dioxide that has been trapped in the soil, in that frozen soil for millions of years, or at least tens of thousands of years, right? So this release accelerates the projected warming because now you're putting more methane and carbon dioxide into the air that wouldn't have happened naturally. It's unnatural because these areas are warming too quick, and so this permafrost is melting. Methane is also in the permafrost on the Arctic seafloor, which again, as that begins to warm, will melt and will release that methane into the air. Then again, we're talking about these rising sea levels, projected sea level rise, 40 to 60 centimeters by the end of the century. Doesn't sound like a lot, but it is. And more than half of the rise is from the melting of the Greenland's ice glaciers there. Serious effects of sea level rise, degradation and loss of 1/3 of coastal estuaries, wetlands, and coral reefs could occur. We know how important they are for the natural capital of the planet. Disruption in coastal fisheries and flooding barrier islands and coastal areas. Again, we talked about how important they are. In addition, you're going to contaminate freshwater coastal aquifers, right? What do we say? Once you get salt into your aquifer, you're done. That aquifer is unusable. And because of sea level rises, that could increase the chance of that salt water getting into coastal freshwater aquifers. The submergence of low-lying islands in the Pacific and Indian Oceans and the Caribbean, right? The Maldives, you may have heard about them. They are slowly going underwater. These people are losing their country, their entire country, because of the sea level rise. Flooding of coastal cities could displace 150 million people. So for instance, if the sea level rises about 1 meter or 3.5 feet, everywhere you see in red here in Florida will be underwater. That means most of Miami, most of Fort Lauderdale underwater, the Everglades underwater, Naples underwater. My retirement home, my parents that I get when they pass, have a home right here in Venice. That home of mine would be underwater, right? So you'll notice Jacksonville underwater, Savannah, Georgia underwater. Okay, so this is what could potentially happen if we reach that climate or those climate tipping points that we spoke about. Ocean acidification, the other carbon dioxide problem. Again, we spoke about it a little bit in a previous chapter. Surface waters have increased acidity by 30% since 1800, could reach dangerous levels before 2050. Carbon dioxide combines with water to become carbonic acid, right? H2CO3. This carbonic acid threatens corals, snails, and other organisms with shells. It doesn't allow the shells to form, right? This is a big issue. It also threatens phytoplankton, which is the primary producer species of the ocean food webs. Without the phytoplankton, the entire ocean food web will collapse. So again, this is a big issue with the carbon, because ocean, it's a carbon sink, but there's so much of it now that we're unfortunately increasing it so much that it's creating this carbonic acid, which is threatening these organisms, which again are very important and very vital. In addition, more severe drought is possible. Like extra heat in the atmosphere depletes soil moisture. When you have less soil moisture, that can actually, another positive feedback effect. Less soil moisture leads to less rain, which leads to less soil moisture, which leads to less rain, which leads to less soil moisture, et cetera, et cetera. So again, it's a positive feedback, which prolongs droughts and make them more severe. Higher temperatures intensify the water cycle, right? Because what do you need? Evaporation, right? It intensifies when it gets warmer. So you're going to have additional water vapor in the atmosphere. And what did I say? Water vapor, even though it's not anthropomorphic, is the number one greenhouse gas. So now you're evaporating more water into the air, which then traps more heat, which then evaporates more water, traps more heat, evaporates more water. Once again, a positive feedback effect that is not positive. You're going to see increased in wildfires if we have more drought. You're also going to see a reduced growth of plant and trees. Again, more extreme weather. The intensified water cycle could bring more flooding to some areas. Annual days of extreme heat in parts of the U.S. will rise dramatically by the end of the century, and some areas may experience colder winter weather due to changes in that global air circulation patterns. Final one for this lesson, for part one, threats to biodiversity. Again, the Amazon rainforest, we could lose 85%. due to global warming. If you remember in a previous unit, most of our biodiversity on the planet are in rainforests. So now if the rainforests go away, you're going to lose all that biodiversity. Extinctions due to loss of habitat. Again, polar bears and penguins. If the Arctic warms or the Antarctic warms too quick, they will not be able to adapt. Species that live at high elevations may not be able to adapt. Corals, we already spoke about that. The bleaching, seeing that happen. And species with limited ranges, they may not be able to migrate, and as a result, big problems for them. Also, increase in mountain pine beetle, just an example, that destroys forests, which then what? Less trees to sequester carbon. And again, another one of those positive feedback cycles that unfortunately are not positive. All right, well, that concludes part 1 of my lecture on Chapter 20, Climate Change. Please make sure to check back in and watch part 2. And as always, thanks for listening.